All right, welcome everybody. Today we're going to talk about lesson number 66, but before we do so, I have a couple of things I want to explain to you and also a couple of disclaimers. So first of all, today we're going to be starting chapter 9, and chapter 9 is all about sequences and series, and today is just going to be an introduction. So just to kind of set the scene for where we've left off, so we just finished all the trig, which was chapters 4 and 5, and then chapter 6, we've actually already done with our trig, the law of sines and the law of cosines. We did that earlier with the chapter 4 stuff. And then the second half of chapter 6, we're not going to do at all. Chapter 7 and 8 are not as important as the later chapters. So we're only going to go back to those if we have time. But for now, we're going to pick up with chapter 9 and then proceed from there. Some other disclaimers. We have officially reached the 1 year mark in terms of when I started making videos last March. So from this point forward, these are videos that I recorded last year. That being said, I was new to the experience. I did not have as good of a device as I have now. I did not have, as much practice as I have now. So while I am going to consider re-recording certain lessons or certain parts of lessons, for the most part, I'm just going to make small edits to try to be a little bit more efficient. So if throughout the videos I refer to something that clearly does not apply to you and it applied to last year, just disregard. I'll try my best to catch those things ahead of time, but if not, just make sure you know that I'm editing videos that I made last March. So a couple of things you might want to watch out for. Tonight's homework is homework 66. It's typed at the end of your note sheet, but I wanted to go ahead and put it here on the front slide just because it's a little bit easier in terms of editing purposes. And again, last year when I made these videos in March, I didn't have a worksheet for every lesson. So I am going to try to work backwards and create them. But again, some things might not match entirely. Sometimes I might make a mistake and the numbers might be off, or there might be things that are in the PowerPoint that are not on the worksheet. So again, just try to be mindful of that and watch carefully. And of course, if you have any questions at any time, let me know. The first thing I want you to consider is, what do you think of when you hear the word sequence? And again, depending on your level of familiarity, a lot of different things might come to mind. Take example, this string of Christmas lights. Okay, you have a couple of different colors that are in a different order. That's one example of a simple sequence. Consider the lockers at school, not only the way that the lockers are numbered, but the combination of the lockers themselves. That's another sequence. Here you have an example of DNA, so the way that the molecules are, that's an example of a sequence. Here you have multiple sequences going on. Not only do you have a change in color, but you have a sequence with the pattern, and you have a sequence with the size of the shapes. So a couple different patterns or sequences going on at once. Here, your concern is mostly with how many counters is there in each of the different steps. You can pretty clearly see that in step 1, there's 1 red counter, where number 2 has 4, number 3 has 7, and then you could, of course, go forward and make predictions about further steps, in this case, number 4. You're trying to figure out the pattern from step 1 to step 2 to step 3, and it's pretty clearly the fact that you're adding 3 more counters each time. It appears you're adding 1 to the top, 1 to the left, and 1 to the right. So again, these are relatively easy sequences that perhaps you might have seen or you would be able to figure out with very little background knowledge. We're, of course, going to focus on mathematical sequences, and we're going to start nice and simple. So here, you're being asked to solve for the missing numbers x and y. You're going to look at the numbers that are given, try to deduce a simple pattern, and then solve for x and y. So if you look at number 1, 23, 26, 29, it pretty clearly appears as though you are adding 3 each time. So if you use that as the pattern to go from 29 to x, you would have to add 3, which means that x would have a value of 32. Then if you were to add 3 again, that would give you 35. Adding 3 again would give you y equals 38. And again, relatively simple things you're able to figure out just kind of using mental math and common sense and not really having to do any calculations or formulas. In number 2, the pattern appears to be that you're going down by 1. So instead of adding a value, you are subtracting a value. So if you're subtracting 1 every time, that would, of course, be 30 minus 1 to give you a value of x equals 29. And then subtracting 1 again would give you a value of y equals 28. Number 3, 18, 14, 10. It appears as though the pattern is subtracting 4 each time. So from 10, if you subtract 4, that would give you x equals 6. Subtract 4 again, that would give you y equals 2. And finally, number 4, 6, 12, 18. It appears as though the pattern is that you're adding 6 every time. So at 18, if you go ahead and add 6, that's going to give you a value of x equals 24. Plus 6 again brings you to 30. And one final addition of 6 gives you y equals 36. So again, these are relatively simple sequences that, again, you could calculate with very little work, but it's a good way for us to kind of get started. Let's talk about the definition of a sequence. So basically, the definition of a sequence means that it has to be ordered. There has to be a first term and a second term and a third term. You want to kind of start thinking of it as a function whose domain is the set of positive integers. So unless stated otherwise, you're going to assume that you always start a sequence with +1 for the first term, +2 for the second term, +3 for the third term, and so on. You are going to denote the term numbers using subscript notation. So again, the first term would be A with a subscript of 1. We call that A sub 1. Your second term would be A sub 2, A sub 3. And if you're talking about the general term, you're going to call that A sub n. So something that's important to note is that sequences can be finite or infinite, meaning that they stop or they go on and on and on. This is mostly important for later lessons where I ask you to add up terms in the sequence. You'd want to think about what that would look like for something that is finite versus something that's infinite. So something that is an infinite sequence basically means that the domain is all the positive integers and it continues to just go on and on and on. If you're talking about the domain being just the first n positive integers, meaning the first 6 or the first 8 or however many I tell you, that of course is a finite sequence. And then note on the bottom here, sometimes we're going to start the sequence with 0 instead of 1, in which case the first term would be A sub 0. That means that the domain can include 0. And again, if I want you to start at a term other than 1, I have to tell you that, or else there would be no way for you to know. So finding terms in a sequence is the first thing that you have to be able to do if you were already given the formula. So for numbers 5 and 6, I give you the formula and I ask you to find the first 3 terms, and then I ask you to find the 8th term. So for number 5, if I ask you to find the first 3 terms, that means that everywhere there is an n in the problem, you are going to plug in 1, 2, 3, and then for the 8th term, you're going to plug in 8. So the value of A sub 1 would be 4 times 1 plus 5, which would be 9. The second term would be 4 times 2 plus 5, which would be 13. The third term would be 17. And the 8th term would be 37. So when I ask you for just regular terms, you plug in whatever the term number is and then calculate. For number 6, you're finding again the first 3 terms and the 8th term. So you would plug in 1, 2, 3, and 8, calculate. And in this case, it appears that the sequence is only going back and forth between 2 different numbers, 4, 2, 4, and then you're back to 2 again by the 8th term. The next thing you have to be able to do, which people have varying levels of difficulty with, is you have to be able to find the expression for the formula, or what we call the nth term. In order for you to do that, not only do you want to write out the list of terms, starting with the first term and ending with the last term, which again, if we don't know what it is, we assume it goes on forever. So we're going to call that A sub n. Underneath each of the terms, I strongly recommend you write in the term number, and again, assume that we're starting at 1 unless the problem explicitly says otherwise. If you write the term number directly underneath each of the terms, it's really the best way for you to try to figure out what the relationship is between the term number, which again is n, and the formula, which we're going to call A sub n. So you're looking for some kind of way that a 1 becomes a 1, in the same way that a 2 becomes a 4, a 3 becomes a 9, etc. This should be relatively simple. These are clearly the perfect squares, which means that your formula for this sequence would be A sub n equals n squared. So for any term number that I asked you to find, the 100th term, the 50th term, you would now plug that in for n, square it, and then be able to calculate. Some people find these very simple. Some people find these hard. Really, practice is what makes perfect. And again, I strongly recommend you start by always writing the term number underneath. So for number 8, 2, 5, 10, 17, etc., and I've written the term number underneath, this is a little bit trickier, but if you were to look back at example 7, there is a relationship between each of the values in this sequence compared to each of the values in number 7. You can actually see that each of the terms in number 8 is exactly one more than it was in number 7. Which means that the formula for this problem says not only are you going to square the term number, but you're actually then going to add 1. For something like number 9, 3, 7, 11, 15, 9, you're trying to see, of course, if there is a direct relationship from 1 to 3, 2 to 7, 3 to 11, 4 to 15, etc. If there is no clear relationship that you can see, then you kind of want to look at the relationship between each of the terms. And I think if you do that, you can pretty clearly see that you're adding 4 each time. If you're adding 4 each time, you know that that has something to do with multiplying 4 times the term number, 4n. So I know that 4n is going to be some part of my formula. Sometimes that's it, and then sometimes you have to make some other kind of compensation. So if I was to multiply 1 times 4, I would get 4. If I was to multiply 2 times 4, I would get 8. You can see that 4n is clearly not the answer, but it's close. In order to actually get each of the terms, you would then have to subtract 1. You'll notice that 4n minus 1, that is really just a version of y equals mx plus b. Y equals mx plus b is, of course, linear. And from this point forward, any sequence that appears to be linear is going to have a new special name, which is arithmetic. So again, anything where there is constant addition is going to look linear, which is some form of y equals mx plus b. Let's take into account number 10 here. So again, here's my sequence, and then I've written the term numbers underneath. You're looking for some relationship between 1 and 4, 2 and 16, 3 and 64. If you're not able to spot it right offhand, then perhaps you're looking for some kind of relationship between these terms here. I think that you're able to tell that in this case, you are multiplying by 4 each time. If you are multiplying by 4 each time, that implies that you are going to have some kind of exponential equation. So instead of having, like in the previous example, 4 times n, you're actually going to have 4 raised to the n. So again, once you realize that that is the main relationship, sometimes that's it, and then sometimes you have to make a compensation. If we go ahead and test it, 4 to the first is 4, 4 squared is 16, 4 cubed is 64, which means that that is correct. This, of course, anytime you have constant multiplication, that is what we call an exponential function. And from this point forward, the fancy way that we are going to say exponential function is a geometric sequence. And anything that is exponential will take the form y equals a times b to the x. Whether or not a sequence is arithmetic or geometric, that's the focus of 9.2 and 9.3. So for now, we're kind of just alerting ourselves to the fact that they exist. Take a look here at number 11. So 2 and then -4, 6, -8, and then 10. So we kind of have 2 different things that are happening here. We have the fact that you are adding 2 each time. And then we also have the fact that there is some kind of sign change going from positive to negative to positive to negative. So because there are 2 different things that are happening, that means you have to write 2 different parts of your equation. So first, the fact that you're adding 2 each time. The fact that you're adding 2 each time is what makes it linear. If it's linear, you're going to write it as a multiplication. So that would be 2n. We know that that is part of our formula. Then if you take a look at the fact that there is a sign change, the easiest way to write a sign change is to write -1 inside of a parentheses. And then you're always going to have 2 options. Either it's going to be -1 raised to the term number, or it's going to be -1 raised to the term number plus 1. The way that you know it is if the first term is positive, then you know that it is always going to be to the n plus 1. If the first term is negative, you know that it's always going to be to the n. If you're not able to memorize that relationship, then you kind of just do a little bit of guess and check. Let's say you had thought that it was -1 to the n. Well, that doesn't work because if you did -1 to the 1, you would get a negative for your first term, and that wouldn't work. So that's how you know that instead it has to be n plus 1. So this entire thing here is what you need for your sequence. I wouldn't recommend multiplying it out. I would leave it separate. Also note that instead of n plus 1, you could write n plus 3, n plus 5, n minus 1. Basically, you could continue on by adding an even number, but to make things easiest, I would always either use n or n plus 1. Again, here is what I said on the previous slide, written explicitly. If you need to alternate signs in your sequence, if the first term is negative, that's how you'll know that it's just to the n. Whereas if the first term is positive, the most typical way we're going to use is n plus 1. Second most typical is n minus 1. And again, you could technically keep adding even numbers to each of those, but let's just kind of try to make everybody's life a little bit easier. We'll do a couple more of these. And again, if there was a magic way that I could allow you to see the right answer of these, I promise I would. Honestly, the only way to really get good at these is practice. So here in number 12, the thing that jumps out to me the most is the fact that this is clearly a fraction. So I'm going to know that my sequence is going to have something going on the top and something going on at the bottom. I notice on the top that there is an alternation of signs between positive and -1. So anytime there's an alternation of signs, I know that it has to do with -1 to the something. Again, generally speaking, if the first term is positive, you always know that it's going to be n plus 1, where if the first term was negative, you would know that it was just -1 to the n. And if you can't remember that, then just guess and check. If you tried -1 to the first, that would give you a negative because you want it to be a positive. That's how you know that it should be -1 to the n plus 1. Then you take a look at the bottom, 2, 4, 8, 16. You can clearly see that you're multiplying by 2. The fact that there's constant multiplication means exponential, so it has to do with 2 to the n. And again, maybe that's it, or maybe there's more to be done. If you go ahead and check it, 2 to the first is 2, squared is 4, cubed is 8, which means that 2 to the n is exactly what you're looking for. How about something like number 13? Again, the thing that jumps out to me the most is the fact that this is a fraction, so I'm going to draw a fraction bar. If you take a look at what's going on here, if you look at the top, so 1 to 2 to 4 to 8, we again have an example of where you're multiplying by 2. So multiplying by 2 implies something to do with 2 to the n. Again, sometimes that's it, and sometimes there's a compensation you have to make. If you see if this is right, 2 to the first should be 2. 2 squared should be 4, 2 cubed should be 8, which means you're always 1 behind. The way that you say 1 behind is you should be raising your 2 to the n minus 1. And make sure that that n minus 1 is all up in the exponent. If you take a look at your denominators, it appears that you are multiplying by 3 each time. So again, constant multiplication has to do with exponential. So 3 to the n is what you would try. Just to see if you're right, 3 to the first is 3, squared is 9, cubed is 27, which means there is no compensation to make. That is simply the answer. So this is one of the most important things you have to be able to do. These different sequences don't really have any special names other than arithmetic and geometric. Once we get to examples that are only arithmetic or only geometric, there will be formulas that you can use. But so long as you have kind of a mix of all different types of sequences, this is really your best bet to write the term number underneath and then look for relationships. Some reminders, anytime you're trying to write an equation and there's constant addition, that means that you are talking about something that's linear, and that is always going to look like a multiplication. Anytime you have constant multiplication, that is going to imply exponential, which means you have to have something in the exponent. So very important that you know the difference between these two. This is one that you may or may not be able to see. And if you are not able to kind of guess what the numbers on the bottom are doing, then this might be something that's new or just something that you need a reminder of. But once I show you, you should pretty easily be able to use it going forward. So first of all, I would take this one and I would rewrite it as 1 over 1 to kind of make it a fraction like everybody else. Again, that implies that there's a fraction bar here. And the tops are all ones, positive ones, meaning there's no sign change needed. And then you take a look at the bottom here. So 1, 2, 6, 24, 120. It doesn't appear as if you are adding the same thing each time. It does not appear as though you are multiplying the same thing each time. So if there's no constant multiplication and no constant addition, those are the ones that are kind of the hardest. You have to look elsewhere. Again, here's a little bit of a reminder. So this denominator is just a 1, whereas this denominator is actually a 1 times 2. This denominator is a 1 times 2 times 3. 1 times 2 times 3 times 4. And 1 times 2 times 3 times 4 times 5. You may or may not remember what that's called. It's actually called a factorial. The way that you show a factorial is you do an exclamation point. So the formula for this sequence is 1 over n factorial, meaning that the top is always going to be a 1 and the bottom is always going to be the factorial of whatever the term number is. So again, it's very possible that you I guess maybe never have seen that, but more likely you just needed a reminder. So let's talk a little bit more about factorials. Again, factorials always are denoted with an exclamation point. You're only allowed to do it for positive integers, and the definition of a factorial is 1 times 2 times 3 times 4, all the way up to whatever n is. Notice here that 0 factorial is always, always, always equal to 1, never a question. The thing about factorials is that they get very large very quickly. So here's just a couple of the first few positive integers. And again, it has to be a non-negative integer for this to work. So always by definition, 0 factorial is 1. 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. And then you can see a couple of others. As I mentioned, these factorials get very big, very fast. By the time you get to just 10 factorial, you already have more than 3 million. There is a way to do these factorials on the graphing calculator. If you want to practice, you would type whatever number you're looking for, then press the math key, then right arrow over to the probability option, and then choose the exclamation point, and that will evaluate any factorial that you're looking for. A couple of different things you have to do with factorials. So in the previous example, you had to be able to use it as part of a sequence. The next thing you have to be able to do is you have to be able to simplify with it. Now for these two examples, you obviously could just plug it in your calculator, but what if you didn't have a calculator, or what if there were variables? So when you're trying to simplify 9 factorial over 3 factorial times 7 factorial, and the first thing you would, of course, want to make sure you know is that 3 factorial times 7 factorial does not equal 10 factorial. Not a thing. Don't try to make it a thing. So instead, you're going to go ahead and actually write these out. So 9 factorial is 1 times 2 times 3, 4, 5, 6, 7, 8, 9. 3 factorial is 1, 2, 3. And then 1, 2, 3, 4, 5, 6, 7. And you're basically going to cross off any of the overlap. So you can see that 1 through 7 crosses off here and crosses off here. You are then left with 8 times 9 on the top, which is 72. 1 times 2 times 3 on the bottom, which is 6. 72 divided by 6 means that this entire factorial simplifies to just be 12. And again, if you had access to a calculator, you of course could just plug it in, making sure that you put the bottom in parentheses, but it's good to be able to know how to do it without. So again, for the second one here, number 16, you can't just say, oh, the top is 11 factorial. That's not a thing. So instead, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, compared to 1, 2, 3, 4, and 1, 2, 3, 4. You would again cancel out any of the overlap. So you're going to cancel out this 1, 2, 3 with this 1, 2, 3. You're going to cancel out this 1, 2, 3, 4 with this 1, 2, 3, 4. That's going to leave you with 5 times 6 times 7 times 8 up top, which is 1680, over just a 4 on the bottom, which means that this factorial simplifies to be 420. So this is how you would simplify factorials that just have numbers. Let's now talk about how you would simplify factorials that have variables. So for number 17, you're trying to simplify n plus 1 factorial over n factorial. When you're simplifying these problems, basically what you're trying to figure out is who's bigger, the top or bottom, and by how much. So n plus 1 factorial compared to n factorial, the top would be bigger because n plus 1 is a bigger number than n. Think about what would happen if you were to write out the top n plus 1 factorial. You would start off 1, 2, 3. You would go all the way up to the final number, which would be n plus 1. Then think about the terms that would precede it. The term before n plus 1 would be n plus 1 minus 1, which would be the nth term. The term before the nth term would be n minus 1. Consider the denominator, which again starts 1, 2, 3, and then goes all the way up to the largest term, which in this case is n. 1 fewer than n would be n minus 1. And then after you kind of figure out what the terms on the top and what the terms on the bottom look like, you'd be trying to cancel out all the overlap. So anything on the top from 1 to n would cancel out the entire bottom 1 through n, which means that all you would be left with is something larger in the top by a factor of exactly whatever n plus 1 is. And it's possible you might not have to do very much work for these, if any, but I want to at least show you how you could write it out if you were looking to. Again, number 18, you'd be asking yourself, which of these is bigger, n factorial or n minus 1 factorial? I would hope that you would know that n is a bigger number than n minus 1. And again, you're trying to figure out how much bigger. So consider n factorial starts 1, 2, 3. The largest number in n factorial would be n. 1 smaller than n would be n minus 1. Smaller than n minus 1 would be n minus 2. And then obviously there's lots of terms in between. If you were to write n minus 1 factorial, you would start 1, 2, 3. The largest number would be n minus 1. The number before that would be n minus 2, n minus 3, and again, lots of numbers in between. You'd then be looking to cancel out all of the overlap, which would be everything from 1 through n minus 1 on the top. That would cancel out the entire bottom, which means all you would be left with is n on the top. So to finish us off, we are going to go back and talk about summation notation. And again, you did quite a bit of this actually in your first round of emergency work. This is convenient notation when you are trying to find the sum of terms in a finite sequence, which means there's only a handful of numbers you would have to add up. Sometimes it's called summation notation and sometimes it's called sigma notation. Either of those is appropriate. Basically, whenever you see that Greek sigma, you know that you are adding things up. You are going to add everything up from the bottom number to the top number, and you're going to plug it into whatever the formula equation is. So in this case, you're adding up all the values from 1 to n. So you'd be adding up the first term to the second term to the third term, all the way up to the nth term. So notice that they use the variable I here. Whatever the variable is called the index of summation. The most common variables used for the index of summation are I, j, k, and n, and usually in the lowercase form. I will kind of use them all interchangeably. So if ever there comes a time where you have to pick a variable, you can feel free to choose any of them, but those are kind of the most typical ones. The number on the top is called the upper limit of summation. The number on the bottom is called the lower limit of summation. And it basically tells you to add up all the terms from the lower limit to the upper limit. And you start off nice and simple. So let's say I asked you to find the sum from the first term to the fifth term of 3i. So notice my variable in this case is I, but again, it could be anything, most typically I, j, k, or n. This means that you are going to plug in for the variable all of the numbers from 1 to 5, including each. So 3 times 1 is the first term, the second term, the third term, the fourth term, and the fifth term. You could factor the 3 out or not, it wouldn't matter. If you go ahead and do the calculation, you get a sum of 45. And our final example, let's say you were asked to find the sum from 3 to 6 of 1 plus k squared. Again, notice we use k this time. So you're going to plug in all the numbers from 3 to 6, including 3 and 6. You're going to always have a 1 to start, and then whatever the term number is, you're going to square it. After you find each of those individual terms, the sigma, of course, means add them up, which means you get a total value here of 90.